Thank you very much. Is the volume correct? Okay. Thanks very much for the invitation. It's delightful to be here. So I'll talk today about the issue of the neutron lifetime, and I'll talk a bit about an introduction to how neutrons decay. I'll discuss the importance of the neutron lifetime in an understanding of the early phases of the Big Bang. A little bit about beta decay theory, how we measure the neutron lifetime, and then talk about what John was saying, which is something become known as the neutron lifetime problem, which I will give some personal digressions and give some dirty little secrets about precision measurements that some people are not aware of. So the first point is a free neutron decays. It goes to a proton, an electron, and an antineutrino. So why does it do this? It's very simple. It does it because it can. And why can it? It's because the mass of the neutron is greater than the sum of the mass of the proton and the electron, and the decay does not violate any other conservation laws, baryon number, lepton number, angular momentum. So it will decay. The question is how long. But that beggars the question is, why is the neutron more massive than the proton? And that's actually something of a question, because in the naive picture of the nucleon, a neutron is made up of two downs and an up. It has net charge of 0, whereas the proton is two ups and a down. It has a net charge of +1. So one would expect that the electrostatic self-energy of the proton, if they're a true isospin pair, would lead to the proton being more massive than the neutron. So why isn't that the case? And the reason is that the nucleon is actually a very complicated system. It's a very fair situation to say that molecules are made of atoms, or atoms are made of electrons and protons, or nuclei are made of nucleons. But it's not so clear that it's fair to say that a nucleon is made of quarks, because actually more than 99% of the nucleon's mass is not made up of the constituent quarks. It arises from the self-energy of the gluons. And so it's really a very, very messy business. And so it's not so simple a matter. And in fact, certainly calculating the nucleon mass ab initio is far beyond anything we can do at this point. One would have thought that a calculation of the neutron-proton mass difference should have been something that had been done a long time ago. But a realistic measurement was only done a few years ago. And I just want to call out, and this was a full calculation on the lattice that included both QCD and QED. And here you can see that the theory says that, as we expected, the mass difference between the proton and the neutron the proton should be about 1 MeV more massive, but the QCD says it's about 2.5 MeV larger, giving a net difference of neutron over proton of about 1.5, which is remarkably good. This was a heroic effort to get to this point. So, and this QCD mass difference really results from a kind of anomaly in the mass hierarchy of the up and down quark, which isn't well understood. So now I said free neutrons decay. Why don't they decay in nuclei? Well, the answer is a lot of the times they do. Okay, that's what beta decay is. It's just simply saying that, for example, you can certainly view the radioactive decay of carbon-14 as simply a neutron turning into a proton within the nucleus. And again, whenever the daughter nucleus is sufficiently lower in mass than it will, and if it doesn't violate some other conservation law, it will decay. So neutrons are stable in nuclei because of nuclear physics structure considerations that make it energetically unfeasible to decay. So why is the neutron lifetime interesting? Well, it's a fundamental process and here are a number of other cases in which the same process as a neutron decay is quite important. I'll talk about this, that in the Big Bang, the early Big Bang and primordial nucleosynthesis, there are a number of cases in which the neutron decay or an inverse reaction is important. I'm told this will come back at some point. Okay. Actually, the dominant energy source in the sun, PP fusion, if you look at it for a little while, put PP going to, this is exactly the same reaction as neutron decay, except it's allowed to be energetically feasible because of the relative mass of the deuteron compared with 2 protons. In type 2 supernova events, you have the transition from a degenerate electron gas to a neutron star. That's basically an inverse reaction, and that's the same reaction. Pion decay is the same. Most neutrino detectors look at neutron proton and detect the electron, the positron track and the neutron, and a range of other phenomena. So it's a kind of the prototype for a wide range of semileptonic interactions. So let's talk about the neutron lifetime and how it's important in the Big Bang. So one thing, when you go on the web, there's lots of good pictures. If you can avoid, you look for pictures of the Big Bang, and if you can avoid the pictures of the TV show, you get lots of nice pictures like this. And I like this one because it shows that the Big Bang was not some uniform expansion that just sort of blew up. It actually was a series of distinct phase transitions as it expanded and the temperature rose. And of particular interest is what one could call the era of nuclear physics, which is from about 1/100 of a second to 3 minutes. This is interesting because this may be the part of the Big Bang that we understand the best. And why is that? Because at this point, the physics is very well understood. The energy is now low enough that there's only the common garden variety particles from nuclear physics are present. The density is low. I mean, it's still incredibly dense, but one only needs to consider 2-body interactions. The particle energies are MEVs, so they're within the range of what we can measure quite accurately in the laboratory, and the cross-sections as a result are well known. So what goes on? Let's start at about, something important happens when the universe is about 1/100 of a second old, or until that point. At that energy, the energy of the neutrinos and all these particles are much higher than the mass difference between the neutron and the proton. So these processes maintain a thermal equilibrium between the number of protons and the number of neutrons. That's just given by a Boltzmann factor from the mass difference. Okay. Now, that's maintained by these these weak processes, which have a very, very strong dependence on energy. I think it goes as T to the 5th. So there comes a point, which is known as the freeze-out time, and it's about the energy of 1 big MeV, when the reverse processes are no longer maintained. The cross-section is just too small. It's slow. At that point, the ratio of neutrons to protons is about 1/3. Now, this is an important point. Suppose nothing else happens, then after about a few neutron lifetimes, there'll be no neutrons left. We'll have a universe that's all protons, only hydrogen. That didn't happen. Now, why didn't that happen? It's because while the neutrons are, this decoupling time is set by the neutron lifetime. It's the same cross-section. But at about 3 minutes, as the neutrons are decaying away, the universe is also expanding and cooling. And there will come a time when the universe cools to the point where the deuteron is stable against photodisassociation. So neutrons are being captured by protons all the time, but they're immediately being photodisassociated because there's a sea of hot photons to dispose of. Once the deuteron is cooled, that the deuteron is stable, very quickly neutrons are captured by protons to form deuterons, deuteron plus neutron to mass 3 to mass 4, and so on. And in only about 10 or 20 seconds, all the neutrons have been processed, and they're essentially had been used up making helium-4. And here's the reactions that go on. I mean, this is all very well known. The reactions that go on, here's a list of the reactions, neutron capture and so on. And the cross sections are very well known, but the rate determining step here is entirely neutron decay. So this is something, this isn't even physics. I mean, I know there's some chemists out there, I apologize, but this is just like a chemical reaction where you throw some ingredients in, heat it up, and let it cool, and you see what comes out. And just run through a network of reactions. And it's an interesting picture to look at. So black is the number of protons. This is an extremely logarithmic scale, so you barely see the reduction in the number of protons. Here's neutrons. This is the region where the neutrons are free decaying. There's a little bit of deuterium formed, but it's not stable, so it disappears, and then some mass 3. And now, as the universe cools, the deuterium becomes stable, and very quickly, we start having the creation of some helium, and after about 30 seconds, we're left with protons, helium-3, and then down at the 10 to minus 5 level, everything heavier. Only up to lithium, of course. All heavier elements are manufactured in stars. So I went to a lecture and heard Steven Weinberg talk about it. He said, after 3 minutes, the helium to hydrogen ratio was set. Nothing of interest has happened since, which is an interesting perspective. But one point I'd make is that the prediction of what the final hydrogen to helium ratio is, the uncertainty on that theoretical prediction is set by the uncertainty, this discrepancy that we currently have in the neutron lifetime. So we want to know the neutron lifetime in order to better understand Big Bang nucleus. Let me change speeds and talk about a very, very sort of an idiot's guide to beta decay theory. So, and let me start by just giving you 3 pictures. The basic phenomenology is what I said. The big advance in the understanding of beta decay came with Fermi's view of a current interaction, where he thought of it as being a neutron and proton, the interacting neutron, proton, electron, and so on. And his picture was, it was something that happened at a very short range, and that was all that was required. Of course, in the modern picture, what we have is, that's quite correct, but the actual interaction is an exchange of W that changes flavor of a down quark to an up quark and changes the flavor of the lepton from neutrino to electron. And of course, it must be charge current to change the down to an up and the neutrino to. So this is, now, if we want to understand the theory of this, let's isolate what would be the ideal weak interaction. Something we can't actually see in a laboratory would be simply the interaction between the charge current interaction between the lepton and the hadron without the spectator quarks in the nucleus. This, we believe, would be, so we want to construct a current Hamiltonian that exchanges flavor between neutrino and electron and down to up quark. Right, so we can pick out whatever appropriate operators would give rise to this. Now, in this, we want to include parity violation in some way. So how do we construct a Hamiltonian that's parity violating? Well, what do you need to have parity? I mean, to have parity violation, I need to be able to distinguish between a right hand and a left hand. So what distinguishes the right hand to left hand? Well, the 2 things that you have in a hand are something that circulates and a direction. Okay? The direction is like a vector operator. The circulation is like an axial vector. So the combination of a vector and an axial vector, a push and a twist, will give rise to something that is parity violating. And the relative sign of the axial vector and vector tells you whether it's left-handed or right-handed. There's a huge body of evidence that that's all that's needed for to explain the weak interaction. That it simply consists of a vector and an axial vector, and it's V minus A, and that's a sign that reflects the sign convention that's used to define the operators for a vector and the operator for an axial vector. And if that's all I had was between the elementary fermions, my weak interaction would be quite simple. I'd have one coupling constant, which is the Fermi coupling constant, and then this form. But that's not what I have. In the neutron, life is more complicated because I have these additional quarks which can be exchanging or interacting all the time, and of course that whole sea of virtual particles is going on. Now, however, the strong interaction does not violate parity. So it can't change my left-handedness into my right-handedness, but it can change the relative size of the vector and axial vector parts. So what we think is that, at least in the low energy limit, the Hamiltonian should still be quite simple, where within the leptonic sector, it's still this pure V minus A, but in the hadronic sector, there will be two constants of order 1 that tell you the extent to which the strong interaction has modified the relative size of vector and axial vector. So if neutron decay is purely left-handed, then we only need two parameters to describe it, assuming we know the weak coupling constant. And this becomes an issue of, in understanding the beta decay, we need to measure two numbers. So just as if the standard model is correct, we need two numbers of order 1 plus the Fermi coupling constant describes everything. The challenge is whether all the phenomenology in semi-leptonic weak interactions are describable by these two quantities. If they're not enough, then we have a problem. Either the theory is wrong, there's new physics, maybe there's scalar tensor interactions, maybe there's a right-handed symmetry breaking, a non-symmetry breaking part. Or if the experiments don't agree, maybe somebody screwed up on the experiment. But there's a problem if they don't, and I'll talk about that. So in neutron decay, the phenomenology is quite simple. What can we measure relatively simply, or in principle? Well, we could have a neutron. We could measure its spin. We can look at the momenta of the outgoing particles. And clearly, we have to conserve momentum here. But one of the features of the standard model is that the neutrino is purely left-handed if it's maximally parity violated. And that means that there's now a perfect correlation between the angular momentum of the neutrino and the momentum of the neutrino, which means that I have to separately conserve momentum and angular momentum, but the fact that the neutrino was always left-handed means there's intertwining of the angular momentum and the momentum. And if you write down this famous alphabet soup, which actually I've terminated at B, but it goes on to S and so on, it's the most general collection of potential correlations that one can see in a nuclear beta decay. So this is the famous one. This is the correlation between the spin and the outgoing beta. That's what the Wu-Ambler experiment first measured in the observation of parity violation. But there are many others. I can have the neutrino momentum, the electron momentum, neutrino momentum, and so on. Now, this, any fool could write this down. You just write down all the vectors. What's a challenge is to say, given a particular model like V minus A, how do I determine what each of these constants are? And that was the great achievement of Jackson, Tremont, and whoops, wrong way. And so if you have a pure vector and axial vector theory that's determined by these two vector and axial vector constants, then you can actually get an expression for the lifetime, which sort of not surprisingly is a quadratic sum of the GA and GV. But all of the correlations depend upon the ratio of GA to GV. So if I measure one of these correlations and the neutron lifetime, these are linearly independent, so I can in principle determine both GA and GV. So what that looks like is, if I plot GA and GV, the lifetime, being a quadratic sum, gives me an ellipse. GA over GV gives me a straight line. So now I'm done. Well, that's not particularly satisfying because they'll always intersect somewhere. And if I want to test the theory, what I want to have is an overdetermined set of data for GA and GV. And that conveniently, in large part thanks to John, Ian Towner, and other people, is there's an important theorem in the weak interactions, the conservation of the vector current, which don't worry too much about this, but it basically says that although the axial vector coupling constant can be almost anything, the vector coupling constant must be the same for all nuclear decays. And that is related to electroweak unification. And it's possible by, for example, studying the lifetime and branching ratios of 0 plus to 0 plus decays, or from decays of kaon decays and the unitarity of the CKM matrix, it's possible to independently determine the GV alone. And now we're in business, because now we've got the neutron stuff and the GV. And so clearly what we want to do is zero in on the intersection point and see whether they agree. So let's do that, and I'll give you a quick preview, and it's awful. Okay, they don't agree. And a large part of the disagreement comes from a disagreement between two different measurements of the neutron lifetime that are on the ellipse. This is a slightly different axis for that plot. So that's kind of part of our motivation for wanting to measure the neutron lifetime. But let's talk about how we measure it. So let's back up a little bit. How would you measure the lifetime of any decaying system, which means that it's each decay is a random event? Well, you kind of have two choices. I mean, the obvious way is I get a bunch of this stuff, okay? I see how much there is. I look what time it is. Wait, see how much is left. It's a perfectly good way of measuring a lifetime. Unless, for example, you're measuring the lifetime of plutonium, which has a lifetime of 20,000 years, and it's very, very difficult to get DOE funding for an experiment that lasts 20,000 years. So if you have a very long lifetime, basically, if you have a very long lifetime, you need a different strategy. And that strategy is I get an ensemble of my decaying species, and I very accurately determine how much I have. And then I put a counter near it, and I look at the rate of decays, rate per unit second. And that rate, that's like looking at the derivative of the decay curve. That rate will be given by the number I started with divided by the lifetime. So if you're measuring the muon lifetime, you'd use the method 1. If you're measuring the lifetime of plutonium, you use measure 2. Now, the neutron has a lifetime of about 1,000 seconds. You can use both methods. Okay, and so we call these, you can summarize these two methods by saying there's the long lifetime, where I fit to the number remaining as a function of time with an exponential k, or the short time, where I look at the rate of decays, is just the derivative of that. In the neutron, I mean, you can describe these two methods by saying this is counting the survivors, and that's counting the dead. Okay, in the neutron case, as I'll explain, this is what's known as the bottle method, and I'll explain that, and this is what's known as the beam method. So let's talk about ultra-cold neutrons. If you don't know about that, I'll explain that, and the bottle method. Okay, are there any solid-state physicists in the audience right now? Okay, please close your eyes and cover your ears, okay? So here is, I'm not a solid-state physicist, so here is my picture of solids, okay? It's electrons on a spring, okay? Now, let's talk about the interaction of an electromagnetic wave passing through a dielectric. So what happens is I have an electric field that's oscillating in time. It excites the bound electron, which is now accelerated, and it re-radiates at the same frequency, but potentially out of phase. What that means is the combined wave that passes by an electron or many electrons will be subject to a phase shift. And this outgoing, that means the total outgoing wave is an increment of many small phase shifts, means a change in the wavelength, which is an index of refraction. So phase shift means index of refraction. Now let's take a different picture, which is the coherent interaction of imagining a neutron passes through a nucleus, and we're not talking about capture in elastic events, but treating the potential scattering of the neutron, of the nucleus. Now, a nucleus appears as a very small, very deep well to a neutron. So neutrons that we're talking about have energies of about a 40th of an eV, whereas the depth of the, so wavelengths of nanometers and energies of little MeV, whereas the potential well of the nucleus is Fermi's and big MeVs. So it looks like a very, very small delta function. Now, all of you have had an elementary, if your elementary course in nuclear physics didn't treat this problem, then you should go back and yell at your professor, because what you find is that in this case, the incoming wave comes in, it's just elementary quantum mechanics. I now have a much shorter wavelength because the energy in this well is much higher. I have to match boundary conditions in the usual Griffith sort of way. And it means the outgoing wave is phase shifted. Phase shift, index of refraction. So a neutron passing through a medium that's not particularly absorbing and doesn't scatter due to inelastic processes will lead to an index of refraction. And here's the problem you should have done in, not at the end. I mean, the energy here is, this is simply, it's gone into a deep potential and comes out. No. The answer is no. No. It's just passed through a potential well. It hasn't, I'm saying this is not an inelastic process. This is an elastic process. It's just potential scattering. That's right. It's coherent scattering. To be coherent, it has to be elastic. So, I mean, there are other processes too. It could have an inelastic scattering, and then all bets are off. Then it's lost. It's gained energy. I'm not interested in that case. I'm talking about the case where it's coherent elastic scattering, which for many nuclei is the dominant process. So this leads to an index of refraction. And again, a problem you should have done in your nuclear physics class is to work out that phase shift can be related to something called the coherent scattering length, B coherent. And that's sort of, this is supposed to be my long wavelength thermal neutron wavelength. Here's the high frequency. And you'd notice I can look at where this long wavelength intercepts the axis and how is it shifted from zero, which it would have been the case if there was no potential scattering. That's called the coherent scattering length, and it's related to my phase shift. And Fermi showed many years ago that the index of refraction can be related to this scattering length. And what's interesting, and I don't have time to talk about it here, is that for very simple statistical arguments, the scattering length for nearly all nuclei are less than 1, and so the index of refraction is greater than 1. Sorry, the index of refraction, I got this wrong. Index of refraction is less than 1. The scattering length is, the index of refraction is less than 1. That means that unlike dielectrics, which have an index of refraction that's greater than 1, which means you can get complete internal reflection inside the dielectric, for the neutron case, you get complete internal reflection. No, you get complete external reflection. So you have a neutron, a material mirror, neutrons will reflect off of it. And this index of refraction, however, unlike the case of many optical materials, is dependent on the wavelength of the neutron. So it becomes larger and larger, or it approaches 0 when the wavelength becomes larger and larger, and you will reach a particular wavelength such that the index of refraction is 0, which means I can get complete external reflection at normal incidence, which means all angles of neutron will bounce off this material. And this wavelength corresponds to a particular critical energy, which for many materials, or selected materials, may be on the order of 100 to a few hundred nano electron volts. That's not a lot. These are neutrons that, well, I used to be able to outrun them, but most of you probably can still. Their wavelength is quite long. It's comparable to optical wavelengths. Now, what's also interesting, in addition to reflecting off of material surfaces, a neutron with 100 nano eV can only rise against gravity 1 meter. So if I drop a neutron from more than a meter, it'll crash through the surface, won't be reflected. But that means if I have low enough energy neutrons, I don't need a bottle. I can make a cup. They'll just bounce up and be confined by gravity. Similarly, in a remarkable coincidence, the magnetic interaction between the magnetic moment of the neutron and a magnetic field for laboratory scale fields is about the same. So if I have a gradient of about 1 Tesla, I can get a neutron to reflect off of it. So I can make a material bottle, a magnet. I mean, this is really cool because you can have confine the neutron by using the strong force. That's what I talked about. The electromagnetic force or gravity. And all have been done, and I'll talk about that. So how do I do a neutron lifetime experiment? It's easy. I take a neutron bottle, just something that can reflect. I fill it up, close it, begin to count, and see how many are left. Right? And that's it. So it's a picture of simplicity. But there's a problem. I will, in fact, measure the neutron lifetime in this bottle. But this bottle might have holes in it. It might have absorbing material in it. And so what I measure is the total lifetime for all processes that the experimental lifetime consists of the beta decay lifetime plus the loss of absorbed neutrons from escaped neutrons, neutrons that interact inelastically and gain energy in it. And so the challenge, it looks simple, but it's challenging because what I really have to measure is somehow figure out all of these and make a correction for it. And that's not always easy. And here's, just to show you, here's a collection of neutron bottle lifetimes. This is what they measured, and that's the correction for all other loss mechanisms. So it's a not insignificant correction for bottle losses. Let's talk about measuring the neutron lifetime with a beam. This is now method 2. How would we do that? So Method 2 is we pass a neutron beam through a detector. It doesn't interact with anything. And then we have a detector that measures the neutron density, not the number of neutrons, because the slower the neutron, the more likely it is to decay. So I have to weight the flux by 1 over the velocity. So I have to, and now I count the number of decay particles. In my experiment, we measured the number of protons. And then we measure the decay rate, and if we know the volume and the decay rate and the velocity, we can determine the lifetime. Now this sounds a lot harder, because here I have to do an absolute measurement of the decay rate, which means I need to know the efficiency of my detector very, very well. I need to know the volume of my detector very well. I need to know the neutron flux and the velocity distribution very well. So we can summarize the two methods of neutron lifetime rather simply. The bottle method appears easy, but it's difficult. The beam method appears difficult and is difficult. Did you have a question? We don't. There are other experiments that have no, we don't. Other experiments are proposing to do that. So I'm going to now talk about my experimental program, which for the last many years, I've been looking at measuring the neutron lifetime in the beam. And we do this at NIST, which used to be NBS. And unknown to a lot of people, the National Institute of Standards and Technology at NIST has one of the most, I would say, the premier reactor facility for neutron beams in the country. It's a 20 megawatt heavy water moderated reactor with a cold source. And it's, I think if the neighbors knew there was a reactor right in the middle of Gaithersburg, but they try to keep that, they don't call it a reactor, by the way. It's called a neutron source. So please don't spread the word. And in here is a whole suite of instruments dominated and mostly devoted to neutron scattering, for using neutrons to understand the structure of condensed matter. But we have a couple of neutron beams. So you can see lots of beams of neutrons that look at a moderator that produces neutrons with energies of a few little MeV. And we measure our decay detector is somewhat novel. So what we do is we pass the neutron beam through a penning trap. Simple idea. In a strong magnetic field, we bias, in principle, 3 electrodes that are biased to with a low voltage, high voltage, and a strong magnetic field axially. Neutrons don't care. They're neutral. They fly right on through. The protons have an endpoint of about 750 eV. So if a neutron decays in this volume, it's stuck there. It will not get out. It's unconditionally trapped. Okay. So now we've got the decay particles stuck there, which doesn't do us a lot of good because it's in the middle of the neutron beam and we have to detect them. Well, first of all, we have to get them out. So how do we get them out? Well, at rather great expense, we've constructed a superconducting magnet that, rather than being a nice uniform solenoid, has a bend in it. So the neutrons come in, pass through happily where the magnetic field lines bend, but the protons, if they escape the trap, are stuck and do tight spirals, literally with a cyclotron radius of about 1 millimeter, and follow the field lines out to a detector conveniently placed out of the neutron beam. Now, the protons only have a few hundred eV of energy, which is not enough to detect, so we bias this detector at 20, 30, 40 kilovolts. So they fall into it, and you can see that's supposed to be them falling in and gaining some longitudinal. So this looks great. You know, it has a nice feature that we can count for a relatively long period of time and then empty for a short period of time. It only takes 10 or so microseconds to empty it. And so our background is reduced by the ratio of the signal to noise by the ratio of the trapping time to the emptying time, and that gives us a factor of more than 100 in background reduction. But there's a problem. What did I say we had to measure very accurately is the trap volume. And this trap has funny end effects. It's hard to even say what the volume is. So we have to know the length of this complicated, and the beam has, the protons have velocity distribution. So we use a trick. We make our trap out of a series of electrodes. We do an experiment. We trap the electrodes. We trap them and then open the trap, let them leak out, and we gain this factor of noise, but we need to know the trap length. So how do we do that? Well, we do multiple experiments. We first do an experiment. We make these trap electrodes very, very accurately and measure them to micron precision, and do an experiment with one number of traps, of trap elements, and then change it. We don't know what the length of the trap is, but we know the change in length very accurately. So this is a way of end effect cancellation that's used quite commonly, and that's immune to the end effects. That's, I think, the Mark III trap. These are gold-plated fused silica electrodes for a variety of fused silica has to be used here. And here's what we see is a slope of decay rate versus trap length. The fact that it's a straight line is, and it's this slope that gives us the lifetime. I'll talk about the results. So now let's talk about the neutron lifetime problem or enigma or anomaly. It depends how you want to call it. So here's the, so this is back when in 2005, when I was much younger and much happier. And you can see here's the bottle experiments in red, the beam experiments in blue. And there was a nice agreement with that. And then my good friend Anatoly Serebrov at St. Petersburg published a bottle result that was here, which caused a great discomfort to people. Huge discrepancy. Following that, all of the Russian results revised their. I'm simply making a statement of fact. The high Russian results either withdrew results or moved their results down. Okay, so now leaving us in a situation where the beam results and the bottle results were in disagreement. Okay, and that was the start of this problem. I mean, you know, we've looked at their experiments very carefully. They've looked at ours. There's no obvious reason for this. I think we all agree they were all carefully done, and we don't know why. This is a particular case of a general theorem known as Siegel's law, which says that a man with a watch knows what time it is. A man with two is never sure. I mean, there's some. This is important. Is if you have a measurement of some quantity and it's measured only once, you're highly dependent on the error that's estimated by those experimenters. And what I'll try to show you is we're not very good at estimating the systematic effects on these precision measurements. It's not from dishonesty or fraud. We're just not good at it. And I'll explain some of the reasons why that may be the case. So let me give a short digression on the precision on the accuracy of precision measurements. So this is my favorite demotivational slide. It's, you know, there's the arrow, splitting the arrow, and it says consistency, it's only a virtue if you're not a screw up. Okay. So I like this idea of marksmanship because so here's a picture of a very good marksman shooting at 100 yards at taking 5 shots, and this is a very, very fine grouping of 5 shots. And let's just look at that. You can immediately see there's two sorts of error in the marksman's ability, in marksman's shooting. One is the shot-to-shot scatter. That's just some intrinsic reliability. That's the precision. Okay? That's easy to estimate. The other is there's a systematic correction because presumably his sights were incorrect. Okay? Now, a good marksman could adjust the shots the next time it came in. As experimentalists, we don't have that ability. What we do is we take a bunch of shots, we can easily estimate the statistical uncertainty, and then we have to think, how was the wind blowing? What do I think the correction was? And I have to make a post hoc correction to see where would I be, and that's hard to do. And as an evidence of that, let me just show you a meta-analysis, not done by me, but you can do it anytime you want, of the best estimates for the fundamental constants. So every 10 years or so, a group of people called the Co-Data Committee gives a recommended value for the values of the fundamental constants and their errors. Now, the new ones recently are so much better than the old ones that they consider to have no error. So I can go back and compare what are now the exactly known values with the values 20 years ago, not because I'm interested in comparing how well they did, but did they estimate their errors correctly? Okay, and the answer is no, they did not. And in fact, throughout and of course, this is, E and H. This is the Olympics of precision measurements. I mean, you don't try to do that unless you think you're really good. Okay, and you can see, in general, even the best in the business seem to be unable to reliably, or seem to have a bias towards underestimating systematic effects. It's not dishonesty, it's not fraud, but it's just very hard to do. And part of it is there may be unknown unknowns that you've forgotten, but it may simply be that the way in which you combine statistical uncertainty, which is known to be Gaussian distributed, with systematic uncertainties, which you have no reason to believe they're Gaussian. Can you add them in as a sum of square root of sum of squares? But I simply state it as a historical fact. We don't do this very well. So maybe the neutron lifetime is an artifact of one. I should be careful. One or more of us has underestimated our systematic effects. There's another possibility, though, and that's very exciting. And that possibility is, what if it's not fake news? Okay, what if there really is there a way to have a physics explanation that would explain the difference between the bottle method and the beam method? And here is something that's very, very tantalizing, because there is a very simple way. Remember, the bottle method looks at all loss mechanisms. So let's assume I've done it perfectly correctly, and I've corrected for the holes in the wall, the gaps, scattering, and so on. But I still see the loss of the number of neutrons. The beam method only measures neutron decay into a particular mode where a proton is created. Suppose there's a neutron decay mode that's not beta decay. That would explain this. And if it had a lifetime, as opposed to the lifetime of the neutron of being 1,000 seconds, if instead it's a lifetime of 2 weeks, that would explain the discrepancy. So this, theorists, here's the point, is if there's a process by which a neutron goes to something but no protons, this would explain there. So what could it be? Well, the first suggestion was it was an oscillation of neutrons into something called a mirror neutron, just like neutrino oscillations go on, and this was suggested. This, I think, is a lot of additional work has been done on it. It is satisfies the the observation of H.L. Mencken, who said that for every difficult and complex problem, there's an answer that is simple, neat, and wrong. Okay, so this is pretty much discredited now. But recently, there's been a very exciting, an idea, I shouldn't say, it's an idea that has generated a great deal of excitement, is that to suggest that there may be alternate decay modes in which a neutron decays sometimes into a dark matter particle that wouldn't be seen in other phenomena. And what was particularly tantalizing is one of the possible decay modes would have a monoenergetic gamma ray. This has been looked for, it hasn't been seen. But it's an interesting idea. But you know, this kind of, I don't know, off the wall, I would say, idea, you can sort of think about, I've always felt it's true that when a theorist publishes a novel result, he believes it, but no one else does. When an experimentalist publishes a result, everyone else believes it, but he doesn't. And I think that's some of the situation we have here. So what did we do? We were very concerned, given that, you know, we're always on the prowl for how we might have screwed up. We thought immediately, how did we screw up at this point? And I thought our weak spot in our experiment was our ability to measure the neutron flux. Because we measured the neutron flux, we have to know the neutron flux. We measured the neutron flux, I won't go into great detail, by having the neutron beam pass through a very thin deposit of lithium, and we looked at the outgoing alpha particles. That cross-section is very well known, so we used the value of that cross-section to determine our neutron flux. This reaction is, and it's very easy to detect with low noise. A concern about that, now we didn't measure the cross-section. We took the cross-section from a regularly updated compendium of neutron cross-sections called the Evaluated Neutron Nuclear Data File. One of the problems with NDEF is the results change. So every time they give a recommended new value for the lithium cross-section, our lifetime changes, which is very unsatisfying. Now, it's not a big change. It doesn't explain the, this, of course, this change occurred after we published our result. So we had to make an adjustment for that. It wasn't enough of a change to explain this. But there's another problem, is that the NDEF results look at all measurements of the cross-section at all energies and determine a best value. And the data that was used, so here's all the data for all the measurements of the lithium-6 cross-section. And that's a fit to the 1 over V, which is a very reliable process if you're far from any nuclear resonance. So it looks like it's a pretty good fit. A concern that we had, whether first is the value really right, but there's another concern is that's the energy regime we were working in. Okay, so you got to worry, you know, is the extrapolation really correct? So we mounted a major campaign which took 5 years and 2 graduate students and a lot of other time to remeasure that cross-section. First principles, after all, this is NIST, okay? So we measured it literally in terms of the meter and the second, okay? With no a priori. We did this through a painful but we think reliable process. And our result was that. I actually have to say I was disappointed at this. I thought that, I thought this would be the discrepancy, and even better, I could blame it on somebody else. But it's not. And what we end up with, this was the result before our recalibration of our neutron flux, and here's how it changed. So the error went down slightly, but no significant improvement in the resolution of the discrepancy. So what do we do now? So there's been a lot of progress. And perhaps the most exciting bit of progress is a very, very beautiful bottle experiment done at Los Alamos called UCN Tau, which had a number of very useful features. It's a magnetic bottle, so there are no wall processes to be a problem. And there was a novel way of detecting the neutrons that was much less sensitive to systematic effects. A very, very pretty experiment. And that they published, their results will be appearing in Science magazine soon. So the current situation looks like this. So here's where we were. This is the new Los Alamos result. In the meantime, my friend Serebrov published a result which is inconsistent with his old result. If he published this result back here, none of us would have started this whole business. Okay, but that's the way it is. There's a preliminary result from a group in Japan who are measuring in a beam by a different method, and it's just very encouraging to see them starting this. They're a long ways from getting down to 1 second, but if you I'd say if you were to point to who do you suspect at this point, I'm afraid it would be the beam experiment. So what about doing a new beam experiment? And we're planning to do that. And let me just say what the enabling technology, yes? No, only the number of neutrons that remain. They do that. They have done that at times, but for that to be really useful, you'd have to detect those protons with absolutely known efficiency, which in a volume that's very large, and it's hard to make a detector that is. It's still it's an enormous volume of hundreds of liters. This bottle is big enough for a couple of people to crawl into. It's a huge. The density of ultra-cold neutrons in that bottle is like 2 per cc. It's not a lot. You need to have a big bottle to get enough count rate. So what about a new neutron lifetime experiment? So actually, our neutron beam was less than a centimeter in diameter because we needed our proton detector to be a single pixel of a silicon detector. If it becomes too large, the capacitance of the detector means the electronic noise begins to become a problem. So we were incredibly limited in statistics because of our tiny little proton detector. In the meantime, there are a number of experiments, the Katrin neutrino experiment, the NAD neutron decay experiment, that have made large pixelated silicon detectors with more than 10 times the size. And by using such a large area detector, we could immediately, with no magic, no new developments, gain a factor of 50 to 100 in our count rate. Now, we weren't necessarily statistics limited, but this kind of experiment, if you want to understand your systematic effects, you have to keep measuring different configurations, different voltages, different things to verify. And each one of these tests has to be done at the same level of accuracy as you want your experiment to be done. So having 100 times the flux means instead of taking a few weeks to do a run, you can do it in a few days, which means you can address your systematics much more thoroughly. So we are proposing to do this at on a new beam line that will give us about a factor of 2 in intensity. That's a help. We need a bigger magnet because it's a bigger beam and with a larger beam acceptance. And we hope that that will allow us to get a sensitivity that's substantially less than that's less than the bottle claimed error on the bottles. And we'll see if, in the meantime, we're continuing to check the systematics on the old experiment, but we don't have the flux unless we build this new experiment. test things. So that's, let me finish by just, so here's a list of all the measurements of the neutron lifetime that I could find, going back to the first measurements of John Robeson in the 1950s. One of the interesting features of this is if you, maybe there's a simple, is that if you fit this to simply an exponential decay, it fits remarkably well. So maybe we shouldn't try to measure the neutron lifetime. Let's just wait a few more years until it reaches its equilibrium. Now, I should point out that as appealing as this notion might be, it has rather severe implications for the Big Bang. So with that, I'll end the presentation. Thank you. I don't have a clue. I mean, I think it depends. It depends what particular. Some processes it might. One of the cases is it claimed that at least some of these decays would perhaps not be affected by the environment of other nuclei. Another concern is what's the implications for neutron stars? And I don't know the answer to that. There's an active, these theorists who proposed the dark matter had a hand-wavy argument why an isolated neutron would be different from one that was in an environment with other strongly acting particles, but I'm not in a position to evaluate that. But clearly that's a, if you can't answer that, then, all matter is going to decay. So that's a question that certainly in the case of the neutron oscillations, there are ways around that from spin-dependent nuclear forces, but there are other problems with the oscillation. Yeah.
But and the branching ratio was like 1%.
Right.
That would be very strange because we do have neutron beams, we should have observed that already. We have gamma detectors around those things, right? I mean, how is that possible that if that's true, then we should have observed that gamma ray?
You're exactly right. I mean, you said if it's true, we should have observed it. Right. I mean.
Take the value that we get from super-loud decay, assume
Yes.
the infinite parity that you can predict what the neutron half-life
Yes.
will be.
So
that half-life corresponds not with the beam measurements,
right.
but with the measurements
right.
of the bond.
Right.
So that would be the beta decay half-life, not the total half-life.
That's right.
So if there were some exotic decay that brought the half-life down, that would conflict with the results from
I think that's right. I think that so what John is suggesting, and this has been described in very carefully by Marciano and Serlin, is if you now go back and say look at the predicted lifetime from the 0 plus decays and the asymmetry and say what do I predict the lifetime is, it turns out to be in good agreement with the bottle experiment, which just says it looks like the onus of this discrepancy is on the beam at the moment. But if it was, this is what the bottle lifetime is what should be in the case of because it's the beam experiment that actually measures the branching ratio to beta decay. So I think you're exactly right. But I mean, this dark matter paper engendered a huge amount of interest for about 2 months, and then now that's subsided.
Did it ever get published, or did it just stay in the archive?
I haven't seen it being published.
In the same vein, does the abundance of lithium tell you perhaps phases between bottle and V?
Not so much, because if you look at all of the processes in Big Bang nucleus go so fast compared with the lifetime that the end abundances depend less on the neutron lifetime than they do on what the baryon density was. And so things are almost insensitive to the details of those final abundances are of the light. It's only those elements that didn't have a chance to interact with the neutron while there were neutrons around, and that's mainly due to the density. So there are three quantities that are really relevant in understanding Big Bang. One is the neutron lifetime, which sets the decoupling, the freeze-out time, and the decay time. The next is the cooling rate of the universe, which depends upon the number of light species like electrons and depends on the number of neutrinos. And finally, there's a logarithmic dependence on the baryon density.
Last question, Greg.
Is it at all feasible to put two of your flux monitors in a beam separated by a long flight path and count the changes in flux?
Absolutely. You could do that, but it wouldn't help because the flight time is so short that the change in count rate would be so small that you couldn't statistically get a meaningful number. You'd need to have miles and miles of beam time. So you could probably in that method detect that the neutrons were decaying, but you certainly couldn't do a precision measurement.
Okay, I think we should thank the speaker. He's going to be down here for a while. So you can Very good.
Well, thank you.
Enjoyed that. Might want to take the mic off
Okay.
before you say it.
Thank you. I appreciate it. That's happened to me.
Yeah, well, there's the famous film, of course, with was it, I forget which comedian finished talking and went to the bathroom. Horrible sounds were projected. Yeah, I really hadn't thought of the argument until just, that I know, as we talked before, that the super loud decay agrees with one, but that actually rules out. If you believe it, it rules out.
Doesn't explain that.
Yeah.
Because it would have to agree with the beam.
It would have to agree. Yeah. So,
Yeah, that's a good point.
hello, John. Met the speaker. This
No.
is Glenn Anulet, Jeff Greene.
A couple of comments. One was that similar to your quote, Siegel's quote. There was one in NIST's or NVS's old low temperature lab regarding thermometers as opposed to timepieces. But the other question was: have you ever seen this plot of the magnetic moment? I believe it was the magnetic moment of the proton.
Yeah.
And it starts out some value, big error bars, and then over time it starts refining, and then it jumps tremendously because they discovered or invented nuclear magnetic resonance.
Actually, if you go and randomly go to the particle data group and pick out any particle property that you want and look at it as its recommended value as a function, they all look like this.
But there it's clear that just different systematic errors.
That's exactly what happens.
And
normally that's a result of when a new result, new method it's better and with different systematics you see a jump.
Yeah. And this exponential decay is just the other argument. Why was this one getting better and better? Is because when you measure something that's close to the previous guys, you stop looking for errors.
Yeah,
There's a psychological reason.
I don't think so, because on the most recent experiments we've been blinding it.
No, I mean,
I think it's also is that all of those early measurements which dominated
Yeah.
decay were
Not a video of this. Okay. I'll ask.
done in the beam method.
Oh, yeah.
And they were largely the major, maybe the major, maybe missing some decays.
Several people wanted your slides. Could you possibly leave a copy with me or mail a
I'll
copy?
mail a copy. I have to remove the politically incorrect.
I'm an astronomer. I teach astronomy, and some of your slides are perfect for lectures in astronomy and also for colloquium too. It was a brilliant talk. Thank you very much.
Talk, yeah.
Absolutely great talk.
And I have the same reason. I'm teaching modern physics, and it's just in the morning I thought beta decay, neutrons and stuff. So it's just my next lecture will be Big Bang. I really need it.
Politically correct.
Well, I don't recall anything incorrect.
I'll send them to John.
Yeah.
What was
Well, some of the jokes, you gotta be careful.
Small question. Yeah, sure. First of all, thank you for the talk. Thank you. I record your talk, if you don't mind, or I could delete it. Because it was required for my class. I recorded, if you don't mind.
That's okay. Better if you don't tell me.
Well, I think it's like your rights.
That's a good observation, John. But I think the dark matter people didn't. Yeah, that came. The Marcion and Serlin paper came after the dark matter. They sort of appeared independently.
Yeah.
But I mean, anyone could have done. You don't need Marcion and Serlin to do that deep.
Yeah.
Just look at the PTG volumes.
Right.
But I mean, that paper was superficial in a lot of ways.
Mm-hmm.
So I mean, its only value in my mind is that it generated a lot of interest.
Of course. Yeah. And I mean, it is. I mean, when you first realize that the beam experiments, if they have a systematic problem, would be in the direction of missing some decays, and then they both argue in favor of some common answer.
Yes, that's right. And it's a very, very appealing notion that it's.
Oh, sure. I mean, we all like marvelous new discoveries,
but I
rather
fear
than mistakes.
I'm not quite prepared to advocate for that now.
No, I agree. And the fact
I mean, you and I know how hard these things are.
Oh yeah, for sure. And I mean, it is. Of course, bigger guy.
Phenomenology.